Okay, I'm sorry. You good?
Yep.
All right. Floaters. Something I'm very familiar with. All right. What if we pretend in our headsies there is some object, who cares what it is, but it is submerged underneath any given fluid. Usually it's water, but it could be anything. There is what we call a buoyant force trying to push this sucker back up, because when this gets submerged into water, it pushes the water out of the way. What that water tries to then do is push itself back to where it came from and elevate this thing out of itself, and that upwards force is what we refer to as buoyancy. It's due to the fact that we have a different amount of pressure up here because we're only that deep up there compared to the depth down here. There's a difference in pressure. Okay? Pressure, we said the other day, is a rho of the fluid, the density of the fluid that it happens to be in times G times an H. And then this is also a rho of G times an H, all right? So those are pressures, which then are also forces divided by areas. So the pressure is also a force divided by an area. So what I can do then is say, okay, forces are what push things. So if I want to take a pressure and turn it into a force, I have to multiply that pressure by the area. So I will put the area there, and it's pressure times area. So this up here is pressure. If I multiply those by areas, then what I end up with is forces. So the force that it's feeling right there is rho G H times A, the height at depth 1. And the force this feels here is a rho G H2 times A. Okay? And again, it's the density of the fluid, not the object. So if that's the case, what we're dealing with, then what we can do is say, well, gosh, I have a rho G A that's the same everywhere for this object. So the density of the fluid doesn't have anything to do with the object. The planet that we're on doesn't have anything to do with the object. And we typically talk about a uniformly shaped object, so the area is going to stay the same. The only difference are those H's. So that change in force is, or the difference in forces, 1 to 2, is equal to the rho times G times the area, because that stays the same, and then the difference in H's, which is a delta H, or just the height of the object. You guys probably can tell that an area times a height.
Volume.
This is a length times a width. That's a height. That's a volume. So this then, the change in force, which we then call a buoyant force, because there's water molecules pushing down, there's water molecules pushing up. The difference in that force is what we call a buoyancy. So the buoyant force is the upward force that is the density of the liquid now, not the object, times whatever planet we're hanging out on, times the volume of the object that happens to be submerged, just the volume that's below the surface. So if part of it's floating and part of it's above the surface, that doesn't take into account, or that doesn't contribute, to the buoyant force. It's just the rho G V submerged. All right, that's really, that's the buoyant force, okay? So, all right, let's, throw something in a fluid. Then one of three things can happen. It could, if this is, say, the swimming pool, right? Throw something in the pool, one of three things can happen. It could sink to the bottom. It could float on the top, or it could kind of hang out somewhat suspended somewhere in the middle-ish. That's easy. And what we're going to then end up doing is saying, okay, what's the buoyant force? What's the gravitational force? Is there a normal force? Is there anything, what are the sums of the forces on these objects? And we can then talk about what is the buoyancy? What would be the tension if we were hanging on a rope? What would be the normal if it's resting on the bottom? is there even a normal in this particular example? So in those three situations, then what we're going to do is figure out what the buoyant force is, what its weight would be, or apparent weight might be. All right? So, in the example of a floater, like these one, then one of my favorite questions, how many arrows do you see? How many forces are tugging on this guy? And hopefully you can say 2. There is still the force of gravity. The planet Earth is stupid. It doesn't know it's sitting in a pool of water. Or you can say the planet Earth doesn't discriminate. It doesn't treat it any differently because it's in water as opposed to not being in water. So that gravity is going to stay. And then the other one is what we just figured out. There is an FB, a buoyant force. And if it's not moving up or down, then it's just like life. Everything adds up to nothing. So that means the sum of the forces in the y equals mass times acceleration in the y. And if it's not accelerating in the y, that's what you just said, it adds up to nothing. There is absolutely nothing going on. So the two forces in the y are an FB is upwards, so that's positive, minus FG, which is negative, equals nothing. Buoyancy equals gravity. Buoyancy, we just said, is rho of the liquid times G times the volume that's just submerged. That is equal to the force of gravity, which we would say is mg. Sometimes, though, instead of using mg, another way to say m is, remember the density formula up here? I can write it. The density of anything is mass divided by volume. What if I do rho now of the object times the volume of the entire object? That would equal mass of the object. So I could, down here, instead of just calling it an mg, I mean, you got options, it doesn't matter. You could call it mg, or if there's something else, a different part of the question, you could call it rho of the object. Now, just don't get it confused with the density of liquid. Times the volume. And again, this would be the volume of the whole entire object, the volume of the object, not the volume that's just submerged. And then times it by the G, sorry, then times it by the G. See? Huh? Then the G's will die. It doesn't even matter what planet you're on. Different questions will ask you different things. What's the density of the object? Or how much of it is above water? How much of it is below water? What's the density of the liquid if only this much is submerged, that sort of thing. It'll give you different amounts of information. Different questions are created similarly but not equally. But those are the things you can put together for a floater. Eh? Treat it like a Newton's second law problem, because it's a Newton's second law problem. What if we have one that's just kind of suspended? It's not rising or it's just sitting there. How many arrows do you see?
2.
It's the same. Yeah, it doesn't make it any different. Yeah, it's the same as this guy. Doesn't matter. There's still an FB. There's still an FG. They will still add up to nothing as long as it's not being pushed up or still in the process of sinking. And for this level of a physics class, we'll typically say, hey, it's sitting there in a nice horizontal. It's not elevating. It's not rising or sinking. So we can still say it equals 0, which means buoyancy minus gravity is still nothing, which means buoyancy is still gravity. But then what changes is the volume that is submerged is the same as the volume of the whole and entire thing. So we can kill more stuff there. We can kill the volume of the object, the volume that is submerged. We can kill what planet we're on. density of liquid, then you'll know is the same as the density of an object, which makes sense. I mean, if you hold a water balloon next to a swimming pool, you'll feel it be kind of heavy, right? But what if you hold a water balloon inside a swimming pool? Its density is the same as the pool, so what's pulling it down is the same as what's pushing it up, so those objects will have the same density, okay? The one that is a little different then is this guy. And for this one, how many arrows do you?
Tree.
3. Oh, tree. See, I said it incorrect.
Lead.
Do you see tree? First of all, again, the planet Earth doesn't treat it any differently. Neither does the fluid. But then the other one you add in is a normal force. It's just like you standing on the floor or whatever, there's still a normal Fn. And so now all of these three add up to nothing still. It's not a floater, sorry, but it still adds up to nothing. It's still just like your life. It adds up to nothing. But there are 3 arrows we put together. And I guess I could do that math over here. I suppose we could say, well, gosh, if these 3 add up to nothing, the 2 that are up are positive. So there's an FB plus an FN minus an FG is how many friends I have. Okay? Remember, the planet Earth doesn't treat this guy any differently than it would if it were outside of the pool, outside of the whatever. It's still going to exert the same force. The buoyancy is still the rho GV submerged. Now, what these questions will usually ask you is, what would that normal force be? And another way of saying normal force is what's called the apparent weight. Okay? Because what if I have this object, let's say, I don't know, let's say it's you, pretend it's me, let's say it's V, okay? And I'm hanging out on the side of that swimming pool on a bathroom scale. Some of you know I weigh a very intimidating 140 pounds. That scale would say 140 pounds. But if I do the same thing down here, will that scale still say 140? No, it'll say a number less than that because buoyancy is pushing me up and it's reducing the interaction between my feet and that scale. So if I step on a scale underwater, it'll say I weigh less. So gosh, apparently I don't weigh 140. I weigh something apparently. That's literally where the term comes from. Another way to visualize it is what if I'm holding a rock on a string with a magic force-ometer attached to the string. Maybe that rock weighs 100 newtons, and then I dunk it underwater. That magic force-ometer will now say a number that's less than 100 because that buoyant force is helping to push it up. So your normal, or your apparent weight, decreases when you're underneath the fluid. So usually if they talk about an Fn, what it would equal then is Fg minus Fb. And then it depends on what they give you. Usually it'll be an mg minus the rho. Now remember, it's the rho of the liquid, not the object, times rho g, the planet we're on, which would end up dying, times the volume of the object that's submerged. And if the whole thing is submerged, then the v is the v of the object. Okay? All right, not too terrible. All right. Plus Fn and G. What about these one? What about these one? All right. Let's do these. Let's pretend we throw a piece of wood in there. I'll redraw it over here. So there's some high quality H2O, and there's some object, a piece of wood. Okay? If it's floating, how many arrows do you see?
2.
So there's still Fg and FB. All right, now what do we know about that piece of wood? Let's call the volume. How much space it takes up. Now remember, we're going to be in cubic meters. And a cubic meter is very, very big. And a chunk of wood usually isn't. So volumes are going to look a little awkward at first until you get used to messing with them. There's going to be a negative exponent on here, but let's call it 1.5 times 10 to the negative third cubic meters. Okay, that's just because we always use the metric system standard of cubic meters. That's why it'll look funny. Let's say the mass of this sucker is 1.2 kgs. Okay? What I'll end up asking you is what percent of it is above the surface, or is out of the water, is visible, maybe is another way to word it. What about percent is above the surface? All right, first of all, if it's floating, we can
Floater.
go here, call it a floater. Where the sum of the forces in the y equals ma, which goes away. The two forces are FB minus an FG is nothing. The FB is the rho of the liquid times the planet we happen to be on times the volume that's submerged is equal to the mass of the object times FG is mg, right? Okay? So with this, I think we can kill what planet we're on, it doesn't matter, and the V sub, we don't know, that's what we'll be solving for. The mass of the wood was given up here. The density of the liquid, if I said it was water, did I? Oh yeah, H2O. So that means you know the density of it, right?
Yeah.
Cool. So the density of liquid, and then we're getting the volume submerged. The V sub is nothing more than the mass of the whole thing divided by the density of the liquid. Okay? So can you tell it's going to be a small number, and what's the density of water?
1,000.
It's 1,000. So the mass of this sucker divided by 1,000, that's going to be a small number. But again, when you kill the kgs, those flip over, and you're going to be in cubic meters. So it's 1.2 E negative 3 is the volume that's just submerged compared to the volume, what did I say, is 1.5 E negative 3. All right? So that's not too terrible. So this will be the V sub is 1.2 E negative 3 cubic meters. That I can just see what percentage of that is of 1.5, which would be like 80-ish, yeah. So then, but that, okay, that 80 is just what's submerged now. So the part that floats is 20, or not the part that floats, but the part that's above it
Yeah.
would be 100 minus that. All right. Then what else? Oh, okay. What if I want to add mass to this? Let's just start stacking. I don't know. Let's just start putting pieces of lead, peanut butter. Yay.
We have 1 minute.
We got 1 minute in this class, or?
Yeah.
Yeah.
Oh, jeez. Time flies when you're having physics. We start adding masses of peanut butter here, and it starts sinking. Then something we could do is say, okay, how much mass do I have to add until its apparent weight? Is 20 newtons. And remember, apparent weight is
FN.
these one. So Fg minus Fb is Fn. So if I call that 20, that's going to equal mg minus, if it's going to have an apparent weight, it needs to be completely submerged, either held up by a string or by the surface of the bottom of the item. So that Fb is the rho of the liquid times the planet we're on, rho g times the volume of the whole thing. Okay? So 20 newtons, then the mass is the mass of the whole thing. G is still that, the density of the liquid is still there, G is still 9.8. The volume of the whole thing stays the same, and you would end up getting a number, just so you know where are we at here, it would end up being 2.3 kgs would be the total mass, or I'm sorry, what did we start? 1.2 was, total mass would be 3.5 kgs to the 1.2 that it already is. So you'd have to add 2.3, multiply that by 9.8, that would call it 23 newtons is how much weight you would have to add to get it to have an apparent weight of 20. All right, sorry, the bell rang, yay physics, I'll see you. Have a great summer. I love physics in the summertime.